All right, let's dive into something that, sounds kind of simple, but is literally the foundation of, well, everything in science. We're talking about measurement. It's not just about numbers, it's the language we use to make sense of the universe. And just like any language, for it to work, we all have to be on the same page about what the words actually mean.
I mean, think about it. How are you going to build a rocket if your meter is just a little bit different from your partner's? Imagine one team builds a fuel tank that's supposed to be exactly 10 meters long, but their meter is off by a tiny fraction, and another team builds the rocket body using their version of a meter. Suddenly, things don't fit. You're not just going to have a bad day, you're not getting off the ground, period. So yeah, having a shared standard language, it's not just important, it's absolutely critical.
And you know what's wild? For a huge chunk of history, the entire scientific world was basically that chaotic rocket team. You had brilliant minds all over the place, but they were all speaking slightly different measurement languages. It was a world of confusion. And it made working together and making real progress so much harder than it needed to be. So, back in the day, you had all these competing systems. You had one group of scientists using the CGS system, that's centimeter, gram, second. Then you had others, especially in Britain, using the FPS system, foot, pound, second. And still others were on the MKS system, meter, kilogram, second. Can you imagine trying to compare notes? It was a total nightmare of constant, frustrating conversions. And let me tell you, that is a perfect recipe for making mistakes.
Okay, so the problem was obvious, right? Science needed a universal language, one single system so that a scientist in Paris could talk to a scientist in Tokyo or Houston, and everyone would know exactly what they were talking about. No confusion, no conversions.
And that solution has a name, the International System of Units. You've probably heard of it as SI. This is it. This is the modern, globally accepted standard for pretty much all science and technology. It's the framework that lets us do everything from building massive particle colliders to tracking climate change on a global scale. It's our universal translator.
So what's this whole system built on? Get this, it's just 7 fundamental base units. That's it. Think of them like the alphabet of the physical world. You've got the ones we all know, the meter for length, the kilogram for mass, and the second for time. Then there are 4 others, the ampere for electric current, the Kelvin for temperature, the mole for the amount of stuff, and the candela for how bright something is. Just 7 letters. Every other measurement we have, speed, force, energy, you name it, is just a word spelled out using this alphabet.
Okay, so we have our alphabet, but just having letters doesn't mean you can write a book, right? You need grammar. And in the language of measurement, our grammar is all about one thing, precision. It's not enough to just say what you measured, you have to communicate how well you actually measured it. And the key to that grammar? A little something called significant figures. Here's the deal. They're all the digits in a measurement you're totally sure about, plus the very first one you had to guess at. So say you measure something and get 1.62 seconds. That number is telling the world, hey, I know for sure it's 1.6, and I'm pretty confident that last digit is a 2, but it's my best estimate. It's basically a built-in way you're being honest about how good your measurement really is. Now, there are a few rules to figure them out, and they're pretty straightforward. Any digit that isn't a 0, it's significant. Easy. Zeros that are sandwiched between other numbers, like the 0 in 101, they're significant too. Zeros at the beginning, like in 0.05, nope, never significant. The only tricky ones are the zeros at the end. If there's a decimal point anywhere in the number, like 100 points, then those trailing zeros count. But if there's no decimal, well, that's where things get messy.
And this is the classic ambiguity problem. Take a number like 4,700 meters. See how there's no decimal point? Those 2 zeros at the end are a mystery. Does this mean you measured it exactly to 4,700, giving us 4 significant figures? Or did you just round it to the nearest 100, which would only be 2 significant figures? The way it's written, we have no idea. It's just bad communication, plain and simple. And this is exactly why scientific notation is a lifesaver. If we write that number as 4.700 times 10 to the 3rd power, all that confusion just vanishes. See? We now know for sure there are 4 significant figures, because we wrote them down. Scientific notation isn't just a fancy way to handle huge or tiny numbers. It's a tool for being perfectly, unambiguously clear.
So let's recap. We've got our alphabet, the SI units, we've got our rules of precision, significant figures. But there's an even deeper layer to this grammar. This is the stuff that makes sure our scientific sentences, our equations, actually make logical sense. And this is where we get into what are called physical dimensions. Now, this isn't about the number itself. It's about the type of thing you're measuring. It's its fundamental nature. We use these little brackets to talk about it. So any length, I don't care if it's a tiny millimeter or a massive light year, has the dimension of length, which we write as L. Any mass is m, any time is t. So something like velocity, which is length divided by time, has the dimensions of L over t.
Okay, so why should you care about this? Because this system is like a secret weapon. It's basically a spell checker for physics. It lets you look at an equation and see if it even makes sense on a fundamental level, before you waste time plugging in a single number.
And the whole thing hinges on one really simple, beautiful rule. It's called the principle of homogeneity, which is a fancy way of saying you can't add apples and oranges. You can only add or subtract quantities that have the same dimension. You can't add a distance to a time, right? That's meaningless. So for an Onwood-Jet equation to be legit, every single piece of it that's being added or subtracted has to have the exact same dimensions.
Let's actually test this out on a classic physics equation. On the left, you have x, position. That's a length, so its dimension is L. That means every single chunk on the right side better end up as a length too. So the first term, x0, initial position, that's a length. Check. The next term, v0t, is velocity times time. Velocity is length over time, L over t. Multiply that by time, t, and what happens? The times cancel out and you're left with length, L. Perfect. The last term is acceleration times time squared. Acceleration is length over time squared, L over t squared. Multiply that by time squared, t squared. Again, the times cancel, and you get length, L. Look at that. Every single term is a length. The equation is dimensionally consistent. It passes the spell check.
But here's where it gets really cool. Checking your work is one thing, but dimensional analysis is way more than just a proofreading tool. It can actually be a tool of discovery. You can use it to figure out how different things in the universe are related to each other. So let me ask you a question that seems, well, impossible. How could you figure out the formula for the time it takes a pendulum to make one full swing without ever actually building a pendulum or doing an experiment, just using your brain and a piece of paper? Well, we can do it with pure logic. We just make a reasonable guess. We assume the swing time, the period, depends on a few things, maybe the length of the string, the mass of the weight at the bottom, and the strength of gravity. So we set up an equation with those things, each raised to some unknown power. Then we do our dimensional spell check. We force the dimensions on both sides of the equation to match, and when you solve it, you find something incredible. The power for mass comes out to be 0, and anything to the power of 0 is just 1, which means the mass doesn't matter at all. The weight of the pendulum has no effect on how long it takes to swing. We figured that out without ever touching a real pendulum. What we're left with is this beautiful relationship. The period is proportional to the square root of the length divided by gravity. We literally just derived the basic form of a law of physics using nothing but logic and our understanding of dimensions. Now, it can't tell us the exact numerical constant out front. You still need an experiment for that little detail. But it revealed the core of the relationship. That's not just cool, that is an unbelievably powerful way to think about the world. So you see, from creating a common language that lets scientists collaborate across the globe, to being a powerful tool for discovering the laws of nature itself, this whole system of units and dimensions is really the unsung hero of science. And here's the thing, this language is never finished, it's always evolving. As we explore new frontiers, from the bizarre quantum world to the vastness of the cosmos, you have to wonder, what are we going to measure next? And how will this universal language have to evolve to describe a universe that we're really only just starting to understand?